Hi, BC Cal. We're going to take notes on 910 today, which is Taylor MacLaurin. It's a lot of notes, so bear with me. But if you could flip to 367 in your notebook, and I'm going to share my screen with you so you can see what I'm doing. Okay, so this is what you should be looking at. And we're going to go ahead and start filling this out. So we're going to start with the function e to the x. And if x is 0, then the y value is 1. If x is 1, we know that our value is just e, or 2.71828. And if our value is 2, here's where you might want to start using your calculator. We get 7.3891. Okay. We're going to go ahead and fill out this chart for all of the polynomials that we see. So this first one is 1 plus x. So if x is 0, it's 1. If x is 1, it's 2. If x is 2, it's 3. That one's pretty basic. The next one, we're not just doing 1 plus x, we're also adding on x squared over 2 factorial and x cubed over 3 factorial. If we plug in 0, it's 1. In fact, aren't all of these going to be 1 when x is 0? Okay. Then when x is 1, we have 1 plus 1 plus 1/2 plus 1/3. And that should come out to 2.6 repeating. And if we plug in 2, we're going to get 6.3 repeating. Okay. And then we already have the results for this much. So we're going to add on x to the 4th over 4 factorial and x to the 5th over 5 factorial. That's going to give us 2.7167 and 7.2667. Okay, so we notice as we move from 1 plus x to this longer polynomial, we're getting closer to this estimate of e to the x, okay? These numbers are becoming more and more similar. And the more terms we add on, the more likely we're going to get closer and closer to these numbers, okay? So, the degree of these power series, that's what they're called, is the highest exponent, okay? So this one, the highest exponent we see is a cube, so it has degree 3. This one, we don't have an exponent per se, but we know that if we just have an x, it's raised to the 1st power, so degree 1. 1 minus x to the 5th over 2 would have a 5th degree. And 5, there's no x at all. So we would say it has degree 0. It would be the same thing as writing 5x to the 0th, because x to the 0th is, of course, 1. Multiplied by 5 is still 5. Okay? And then finally, this one down here, we have 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial. And we go all the way into an n value. Okay? So we would say this has degree n, or it's an nth degree polynomial. Okay, so that's a power series. And it comes from this definition we see down here. We would say that the power series is centered at a constant c, where that x is subtracting c, and c is that center. Okay, so let's practice with these down here. this one is x subtracting anything, or is anything subtracted from x? No, so what we would say it would be centered at x equals 0. Okay, this one we see a +1. Okay, so we have x plus 1, x plus 1 squared, x plus 1 cubed. Now, notice in this format it was minus c, and now we have a plus c. So really, we could say this is minus a -1, because if we had x minus a -1, we would say that's the same as a plus. So we're going to say this is centered at -1. And then this one, where I'm actually subtracting 1, is centered at x equal 1. Okay? And flipping that right over, we're going to start looking at Taylor polynomials. Taylor and MacLaurin. But a Taylor polynomial has this kind of format where we have f of c, and then f prime of c times x minus c, and then we take the second derivative times x minus c squared over 2 factorial, then the third derivative times x minus c cubed over 3 factorial, all the way to the nth derivative times x minus c to the nth over n factorial. Okay, so that's called a Taylor series. The MacLaurin series is the same thing, except for MacLaurins are always centered at 0. Okay, so if I wanted to write a MacLaurin polynomial, so centered at 0, for e to the x, it's actually not that bad. Okay, so we're going to do a first, second, and third degree. So that means we need to take the first, second, and third derivatives. So I'm going to come over here and start taking derivatives. So f of x we know is e to the x. That means f prime of x is also e to the x. F double prime is again e to the x. And f triple prime is e to the x. Okay, so we have our derivatives, and those were pretty easy. We use e to the x a lot with Taylor-Maclaurins. Okay, so then when we want to write our first degree polynomial, we're going to denote polynomials are always p of x, and the degree we can put down here with a subscript of 1. Okay, so that would just be f of c. Remember, c is for for MacLaurin is 0. So we're going to do e to the 0 plus the first derivative, c, which is e to the 0 times x, plus the second derivative, at second derivative at 0 times x squared over 2 factorial, plus the third derivative at 0 times x cubed over 3 factorial. Okay, well, all these e to the zeros are really just 1s. Okay, so my first degree polynomial, my first degree should only go up to this x equals 1. This is my third degree. So we're just going to scratch that out. So my first degree polynomial is just 1 plus x. You can probably guess my second degree polynomial now goes up to this x squared over 2 factorial term. And my third degree is the whole thing there. Okay, so again, the highest degree polynomial, if I have a first degree, it should only have a power of 1. And that's my bad on that. If we had to write a general term for this, we would write a series where n starts at 0 and goes to infinity. And we know n starts at 0 because we have this 1 term. Okay. So this would be my 0 term, per se. And then when we're writing what this is, what I really have is x raised to some power of n over its factorial, because this is over 0 factorial, which is 1, and this is over 1 factorial, which is also 1. Okay? So then this one, we want to write a 4th degree Taylor polynomial for e to the x centered at x equal 1. Okay, so it's going to change up a little bit because we're not centered at 0 anymore. We're not a MacLaurin polynomial, we're a Taylor. Okay, but I'm going to start by doing the same thing. I have 4th degree polynomial. I need to take the 4th derivative. Again, these are e to the x, so it's pretty basic. Okay. And then I want to go ahead and start plugging in ones. So f of 1 is e, and in fact that carries down to the 4th derivative, which is also be e, okay? So we're not really changing. Then for a 4th degree polynomial, we have, if we look back up at that definition at the top, we need to take f of c, okay? So f of 1 is e. And then we're going to do f prime of c, which f prime of c would also be e, times x. This time it's centered at 1, so I need to subtract a 1 here, okay? Then I do f double prime of c, so f double prime of 1 is e, times x minus 1. This one's going to be squared over 2 factorial, and this whole thing can be over 2 factorial, it doesn't really matter. The 3rd degree would be e x minus 1 cubed over 3 factorial. And then I'm not going to have room for the 4th, but it would be e x minus 1 to the 4th over 4 factorial. Okay? If we're writing a general term, remember we're doing our sigma from n equals 0 to infinity. I always have some kind of e times x minus 1 raised to a power of n. Okay? And I'm always dividing by an n factorial. So this is a general form, depending on where it's centered and what your derivatives are, for how to write the general term, okay? And then my polynomials follow the same format every time, okay? So sine and cosine work a little differently, but it's also not terribly hard. So we want to find a MacLaurin polynomial for sine x. It doesn't tell us what degree we're going to. But the nice thing about sine and cosine is that, okay, if we start with sine, my derivative is cosine. And then my second derivative is negative sine. And my third derivative is negative cosine. And then it'll start repeating, okay? So if we list out, and this is MacLaurin, MacLaurins are centered at x equals 0. So if we're going to list out f of 0, sine of 0 is 0. F prime of 0 would be cosine of 0, which is 1. Double prime would be, again, a sine, so 0. The triple prime is now going to be a negative 1. And they're going to keep following this sequence. Okay, so I listed out the first 7 derivatives just because I can follow that pattern pretty easily. Also because when we start filling in the polynomial, you're going to notice that it shrinks out pretty quickly. So we're going to start with p of x, and we're not writing it to any degree, so I don't necessarily need that subscript. F of 0 is 0, so that's my first term. Then I have 1 times x to the first, so just x. Then I take f double prime of 0, so 0 times x squared over 2 factorial, plus, or I'm sorry, that's going to be a plus a negative or a minus 1 times x cubed over 3 factorial. And then my fourth is 0. Plus my fifth. Okay. Plus 0 for my sixth. And then minus 1 for my seventh. Okay. So you'll notice half of these terms are really just zeros. So I can start taking them out and simplify my polynomial. So really I have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. So I have a degree 7 polynomial, but I only have 4 terms at this point. Okay. Again, we want to practice writing that general term. So I'm going to take my sigma from n equals 0 to infinity. One thing we notice about this is it alternates positive, negative. So I need to throw my alternator in there. Okay. Then because I want to ignore the even terms, I'm not going to just write x to the n. Okay. I want to write only the odd terms. So we have to go back and kind of think algebraically. If we want an even number, any even number is n times 2. Okay. Doesn't matter what your n is. If we multiply by 2, it'll give us an even. Okay. So we don't have even powers, though. We have odd powers. So to make it odd, we're going to take that 2n and add 1. Okay. Because any n times 2 will give us an even, plus 1 will make it odd. Okay. So if I only want the odd powers, I'm going to raise x to the 2n plus 1. And then I only have odd factorials on the bottom. So I'm also going to do 2 plus 1. I'm going to put that in parentheses before I write my factorial. Okay. So we're going to do the same thing for cosine. And as you can guess, we're going to end up with something similar, but very, very different. So we start with cosine x. The prime is then negative sine. Double prime is negative cosine. And triple prime would be sine. So when I write f of 0, because we're doing a MacLaurin still, cosine of 0 is 1. Sine is 0. Sorry, that should just be a double prime. Double prime is negative 1, and then now my triple prime is 0. Okay, so this time, our first term is not going to be 0 like it was up here. My first term for p to the x is going to be 1. But then my second term is going to be 0 times x. My third term, I have a negative x squared over 2 factorial, because I have that negative 1. And then we'll have 0 for x cubed, a positive x fourth, a 0x to the 5th, a negative x to the 6th, and a positive 0x to the 7th. So this time, instead of all my even terms dropping out, all my odd terms have dropped out. Okay, and we still notice that it's alternating positive and negative. So when we write our general term, we're going to throw that alternator in there. This time we do want even powers. So instead of 2n plus 1, I'm going to use my even. So 2n over 2n factorial. Okay, so let's make sure you can see that. Typically, I make you memorize the MacLaurin series for e to the x, sine x, and cosine x, up to 4 terms. So not 4th degree, but 4 terms. So this we would memorize. This we would memorize. And then the e to the x, which we did here, we would memorize. Okay. Since we're at home for the foreseeable future, you're going to have your notes with you. You probably won't memorize it. But if you were to take a Cal 2 class at college, they're going to make you memorize it. So it might be good to start working on that. They're not hard to memorize. You could do it very, very easily. Okay. So this kind of just reviews down here the definition of an nth degree Taylor polynomial. You had that on a previous page too. And then looking at what happens when c is 0, then we take f of 0, f prime, f double prime, f n to the prime. Of course, if c is 0, then it's a MacLaurin polynomial. Okay, they're named after 2 different mathematicians. If you find mathematicians interesting, you can go ahead and look at that. This is going to go ahead and review just a little bit. So this first example, a 3rd degree polynomial for e to the x. We've done this before. At this point, we've in doing this kind of lesson, we would have had it memorized. So we would say 3rd degree polynomial is going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Okay. And we're going to use that answer that we had memorized for A to go ahead and solve part B. Because it's asking what happens when we take f of x, subtract 1, and then divide by 2x, and what happens to that limit. Okay. So I'm going to go ahead and plug in for f of x. Okay, so we get something like that. You'll notice that those 1s are going to cancel. And now that I'm using my Elmo to teach from home, we'll use some pretty pens to cross this out. Okay. So this is what I'm left with. If we were to do, because if I plug in 0, I'm going to get an indeterminate answer for my limit. So I need to do L'Hopital's. We're going to do this pretty basically. Derivative of x is 1. So let me go ahead and rewrite my limit. We'll tell you we're doing LHOP. X squared is 2x over 2 factorial, which would really just be x. And then this would be 3x squared over 3 times 2 times 1. So those 3's are going to cancel, and we'll just have x squared over 2 factorial. So really just when we take a derivative of a MacLaurin like this, your 1 falls out, and then everything kind of drops down 1 space. And then the derivative at the bottom of 2x is just 2. Now when I plug in 0, these will drop out, my 1 will not, my 2 will not, and I get 1/2. So there's my limit. Okay? Feel free to pause at any time if you need a little bit of a brain break. I know this is a long lecture. Okay. So for this next example, we want a 3rd degree Taylor polynomial for this polynomial that we see. And we're going to find, to start, we're going to find the values of the derivatives. Okay. So if I plug in just f of 0, these terms are going to drop out and I'll just have 2. If I take the first derivative, I get negative 10x plus 24x squared. And if I take the derivative at 0, that's 0 because both my terms have x. My second derivative if I'm using a Taylor polynomial, I can kind of cheat my way through to get an answer. So I'll do f double prime at 0 times x squared over 2 factorial, because that would be Taylor. This one would have just been f prime of 0 times x, which was also a 0. So either way, we were going to get a 0. So f double prime of 0 times x squared over 2 factorial is going to give us negative 5 and then f triple prime of 0 x cubed over 3 factorial is going to give us 8. Okay. If I just want to find the second derivative at 0, I can do negative 5 times 2 factorial, because really this would be my second degree of the Taylor polynomial. So that's how I got that negative 5 times really an x squared. But we know that x is 0, so that's going to drop out. So to solve for f double prime of 0, I'm going to multiply negative 5 times 2, which will give us a negative 10. This one, same thing, this is going to drop out. So I really had this 8 from over here times x cubed, but those x cubes dropped out. So I can, if I just want the third derivative, I can do 8 times 3 factorial, which is going to give us 48. So those are my first, my f of 0, f prime, f double prime, and f triple prime at 0. Then it asks if we have a local minimum, maximum, or neither at x equals 0. Okay. The problem is when we have, so this is going to go back to calculus house. Okay. If we look at our first derivative, one, there's no x term, so this has to be 0. If the first derivative is 0, we don't know what's really happening. So we definitely don't have enough info for a first derivative test. And that's because x prime is equal to 0, but we don't know, does it switch from positive to negative or negative to positive? Okay. If we do a second derivative test, though, because we do have more information there, we know f prime of, we'll call it a, is 0. F double prime is positive. Or, I'm sorry, hold on. If f double prime was positive, then we would say it's concave up and has a relative min. But that's not actually what's happening. Remember, we have a negative. So what's really happening is that it's concave down and has a relative max. Okay. If the second derivative was 0, what do you think would happen to our test? Probably the same thing that happened to our first derivative test. We would say it's inconclusive or not enough information. So we know this is what's actually happening. Is the second derivative is negative. So we would say that f has a local max at x equals 0. Okay, and that would be our answer. Almost done. So this is wanting a 6-degree polynomial for cosine. Again, we should have these memorized at some point. Remember, cosine is the one that alternates with even powers. So when I set up my p of x, I'm going to start with 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Okay? So there's our answer. We're going to use that in part B to integrate this. This is extremely hard to integrate. Okay? Try it. You might have to use your calculator, but if you were having to do it by hand, it would be very, very hard. So instead, we're going to plug in for cosine t our MacLaurin polynomial. So we're going to have the integral from 0 to 1 of 1 minus, it comes out of ink. Hold on. Switch it out. 1 minus, and it wants it in t, so I'm just going to change my x's to t's. T squared over 2 factorial plus t to the 4th over 4 factorial minus t to the 6th over 6 factorial. And then that's all over t squared dt. Again, these ones are going to cancel because it's 1 minus 1. This negative, though, will distribute through. Okay, so that means I'm going to change my signs. So I really have the integral from 0 to 1 of t squared over 2 factorial minus t to the 4th over 4 factorial plus t to the 6th over 6 factorial divided by t squared. All of these have a t squared that we can take out. So then I would be left with 1 over 2 factorial minus t squared over 4 factorial plus t to the 4th over 6 factorial. So I've taken out a t squared. And I'm going to, as you probably have guessed, cancel that with the 1 in my denominator. okay? So I really just have the integral of this mess, okay? When you take the integral, we're going to treat these as the constants they really are. So 2 factorial is 2, 4 factorial is, oh, boogers, almost 72-ish, somewhere in there. We'll figure that out. So when I integrate, I have 1/2 t, because remember I add my t's back in, minus t cubed. And this is where I'm going to write it as, because I multiplied by 1/3, so I'm going to write it as 3 times 4 factorial, which is my 72, plus t to the 5th over 5 times 6 factorial. We're evaluating from 0 to 1. So 0, everything drops out. 1, it does not. So 1, it's 1/2 minus 1 over 72 plus 1 over 5 times 720, and we can multiply that out. It's pretty big. We want to know, we want an error approximation less than 1 over 500. These are both less than 1 over 500. But if I multiply 5 times 720, I'm probably not going to get 500 down here. Okay? So my error, the absolute value of my error, is to be less than 5 over 720, less than 1 over 5. Okay? So then 100, so this won't work. So the estimate we're just going to take the 1/2 minus the 1 over 72, since this one is too big, it falls outside of our range. If we do 1/2 minus 1 over 72, we're going to get 35 over 72. If you were to go ahead and do this in your calculator, the integral, you're going to get the integral equal to 0.486. The way we just did it, when we got 35 over 72, if you plug that in your calculator, you get pretty close to 0.486. Your error, which we have up here, divide that out, is going to be 0.00027, which is incredibly small amount of error between this and so really doing it with the Taylor, if you don't have your calculator, or on the AP exam where you're not going to have your calculator for this kind of problem, doing it with the Taylor polynomial or the MacLaurin polynomial and getting this estimate is your best bet, okay? And they like to see these worked out like this. For homework tonight, you're going to do these 7 problems. It's on page 373 of your notebook. You can just do them on notebook paper, scan them in, and submit them on Blackboard. Okay, thanks for watching.